Great.
So.
Okay, awesome. Thank you everyone for coming. As you all know by now, we are very, very excited to have our esteemed speaker, Stephen Miller from Williams College, here to join us. For Yale alumnus and former math Young's member.
We didn't have Young's back then.
Right.
Yeah, it was just math club. And we only had 2 co-presidents until the semester when both co-presidents had to do, oh, this is being recorded a while, both had stuff right before the talks. So I created the position of secretary, which was held by a string of pre-med students who wanted to pad their resumes.
I don't know if anyone on the board is pre-med, but maybe we should bring back the position. But anyways, he's here to talk about the German take problem. And feel free to help yourself to pizza during the talk, and if you didn't, explain it afterwards. Take it away.
Okay, thank you. So it only took me about 20 plus years to go from where you are to over here. So it's been a while since I've been in this classroom. It's always fun to return to campus. I'm also the director of the Williams College Summer Research Experience for undergraduates. What that means is I get to do all the administrative work, but I also get to run a group. So if anybody is interested in undergraduate research, I'm happy to chat after talk today about that. And if you're interested in applying, just send me an email. I'm happy to discuss with you possibilities. What I want to do is I want to talk about one of my favorite problems. I'm curious, how many people have heard of the German tank problem? All right, if you know a lot of the details that you are forbidden from answering, but it seems like most people will be able to play a fair game. All right, so German tank problem. So the figure on the left is Europe at the start of the major hostilities of World War II. The right is less than 2 years later. And if you look at the map, even cursorily, you can see that the area of German control has expanded tremendously. It's beyond the scope of this talk to talk about why there are some white patches still. I'll leave that for your history classes. But it was a real concern for the Allies as to how quickly the German armies were moving. A lot of this was the German excellence in tank tactics. And so if you are fighting someone with tanks, it would be useful to know how many tanks there are. So this is a German tank production factory. One way for the Allies to find out how many tanks the Germans have is just ask her, excuse me, do you mind if we come over, take some pictures, and get a sense of how many tanks you're producing? Not going to happen. So what are your thoughts as to how the Allies could figure out how many tanks the Germans have? What could you do? How could you find out this information?
Count the tanks.
So count tanks. So which tanks would you count?
The ones you see.
The ones you see. So after a battle, you can look and see how many tanks did you observe. Another thing you could do is employ spies. It's good that all of you are just such nice people. You would never even think of spying, or you're so good you know not to say that out loud. So now, who do you think did better, spies or the mathematicians, statisticians? Of course. Who's giving the talk today? This is not a talk by somebody at the CIA. Back then it was the OSS. This is a talk by a mathematical statistics person. So clearly we're going to win in the end. So I'm going to concentrate on the German tank problem. Does anybody know what other kind of tank problem you could consider, especially on this campus? Sorry? There's other tank problems you could consider on this campus. So I quickly went to the university store. They didn't have any, but the store next door at least had a moisture. They did not have a large. I just quickly grabbed the small and the extra large. One of my kids is going to luck out tonight. So this is the lipstick. How many of you have enjoyed the lipstick? And in fact, one year when I was here, the lipstick was on tour. We couldn't believe it. People actually wanted to see it in other parts of the country. And we said, we'll meet you at the Void at 7 o'clock. So it's really not that hard to understand the lipstick tank problem. There's only one of them. They're not going to make another. The one in mathematics, the one in history, is imagine you observe a couple of tanks with serial numbers S1, S2, Sk. Can you estimate how many tanks were in theater? I will make some assumptions. I don't want to make any value judgments on any people or cultures. Let's just say for some reason, the people who are making the tanks have the serial numbers consecutive starting with 1. It will make things a little easier. This is how the problem is normally done. Afterwards, we can discuss a generalization, which I was surprised that no one had done before. Well, what happens if they're consecutive but they don't start at 1? What would the formula be to predict? So at Williams, we require all of our students to give a 30 to 40 minute colloquium to graduate. And the reason is almost none of our students go into BIME anymore. They're going to have to talk to people. I've had a lot of students over the years do this, and we were looking at, well, how could we extend this? Now, another way you could extend this is, rather than having the serial numbers consecutive, they could be random numbers. And if you do random numbers, then it's going to hide what's going on. There's a lot of places in the real world that do this because they don't want to give away information. If you're trying to make people believe your product is popular, oh, I have the third one. But wow, I have the 197, that looks very different. If you do push-ups, 98, 99. So you can often change the numbers to change people's baselines. Put money in the tip jar, at the start of the night. So a lot of issues with trying to estimate what is the right amount. Now, it's actually convenient if the numbers are consecutive. You can then have the numbers often encode things. Maybe these digits are when it was made. And then you can quickly look at the serial number and see which parts probably need replacement. Right. So the original formulation, the tanks are numbered 1 to capital N. The largest we observe is little m, and we want to estimate what's our best guess for the number of tanks produced, or the number of tanks produced. And the new version is the number from N1 to N2. Now, there are dangers of overestimating and underestimating. Can anybody give me a danger of either? What would be bad if you overestimated? What would be bad if you underestimated? Yes.
If I were to underestimate how many things there are, then under repair, I say, oh, there are going to only be 5.
Yes, only going to be 5 tanks. We'll have no trouble defeating them. And then you see your 200 maps in front of you. So that's the danger of underestimating. What's the danger of overestimating? Yes.
Probably you may put too much human resources or expenditure on the defense rather than making some weapons.
Yes, and in fact, we have a great quote from the Civil War. There's many different iterations of this. Lincoln, if General McClellan isn't going to use his army, I'd like to borrow it for a time. Is that McClellan always believed that he was opposed by a superior force. And I just need a few more troops before I can attack. And there was always a need for a few more troops, And so if you overestimate, there are consequences of that as well. Hello, welcome. So grab some pizza. So for those who just walked in, the basic problem that we're doing is we observe some tanks numbered from 1 to n. We observe m is the largest serial number, and we want to try to come up with what is the best estimate for n. So this is really an introduction to statistics. How many of you have taken stats? I took it from the psych department here. I will not say anything further as it is being recorded. I used to tell my students, if you knew probability, statistics, and computer science, you would always get a job. I can no longer say this because somebody actually sued her institution when she didn't get a job upon graduation. Now, with the Freedom of Information Act, you can actually download the lawsuit where she misspells words like tuition and comes up with a new protected class, students with low GPAs. And said her 2.6 was just as good as someone else's 3.6. So I will no longer promise jobs if you know probability, statistics, and computer science. I will just say, if you can do all three and you don't get a job, I'll be shocked. Okay? You may not like the job, I'm not promising that, but you will have people who will care about those skills. And one of the whole themes of today is how do we actually do some of these problems? What are the tools and techniques? So we talked about the underestimating and overestimating. So we're going to do a little mathematical preliminaries. We'll then do the original problem. I'll talk a little bit about how you generalize. It's essentially just more algebra. And then as time permits, I'll talk about an introduction to statistics, regression, and conjecturing. And so the older you get, the more important you realize it is to be able to make a good conjecture, to get a sense of what the answer should be for a problem. And I'll show you ways to split things out. So mathematical preliminaries. I'm hoping everybody has seen all of this stuff. So n factorial is the number of ways to arrange things, n objects in order matters. So 3 factorial is 6, 0 factorial is 1. There is one way to do nothing. Anybody want to be a smartass and tell me what negative 1/2 factorial is?
Is it root pi?
Yes, it is root pi. So it turns out the factorial function can be extended to all real numbers, in fact, to almost all complex numbers. And in some sense, yes, the factorial of negative 1/2 is the square root of pi. It comes up in the bell curve, the normal distribution of Gaussian as the normalization factor. N choose k is the number of ways of choosing k items from n when order doesn't matter. So think representatives in Congress, If you were doing student council officers, then there would be a difference, and that would be just, n times n minus 1 times n minus 2. And then the last is the binomial form. X plus y to the n is the sum of n choose k, x to the k, y to the n minus k. Lots of different ways of proving this. All right. Has everyone seen Pascal's triangle? All right, I'm going to hopefully show you some new ways to look at it. And the reason we're able to get nice formulas for the German-Tank problem at the end of the day is because of some beautiful identities. So the first is that every number is the sum of the numbers above to the left and above to the right. So n plus 1 choose k is n choose k plus n choose k minus 1. There's a lot of different ways to prove this. I like to prove it by telling a story. So we'll assume we have n Red Sox fans and 1 Yankee fan. So how many people do we have total? N plus 1. Imagine you want to form a group of k people. Well, if I want to form a group of k people, I can choose none. I can not choose the Yankee fan, which is great, and I'll have all Red Sox fans. The ways to do that is 1 choose 0 and choose k. And notice the bottom sums to k and the top sums to n plus 1. I'm accounted for everybody. Or I can choose the Yankee fan, and now I have to choose k minus 1 remaining people. So this is a nice story proof of Pascal's identity. All right. There's a lot of other relations and a lot of other facts you can do. How many of you have looked at Pascal's triangle through the thin lens of modular arithmetic? Okay, so let's see a few hands there. So what we're going to do is we're going to say, I really don't care too much about numbers. I just care, is it even or odd? And so if it's odd, I'm going to put a dot. If it's even, I'm going to throw it away. And you get the following. Now, I've rotated the triangle 90 degrees. The reason I've done this is I wrote the code to do this in Mathematica because I couldn't find something else, and it was just easier to code it this way. I'll show a simulation in a moment. Does anybody recognize the shape? Yes?
Sierpinski's triangle.
Yes, Sierpinski's triangle. So it's amazing the structure that comes into this. And so you can go a little bit further. And now I should be able to toggle now to okay. So what I'm going to do is draw Pascal's triangle, and I'm going to put a dot wherever it's odd and blank wherever it's even. Now the problem is as you go and have more and more rows, I see the Yale budget hasn't improved since I was a student here, and you still have these finite size projection suites. So what we will do is we will constantly shrink the number of rows we have so it always fits inside the same rectangle. And then we will just play it right now. So it should work. So I'll mute that for now. And so you can see, almost like when the Imperial Star Destroyer coming in, here is Sierpinski's triangle coming out. And you can see all the rows being added one at a time. It's a nice programming problem as to what is the most efficient way to write this. So for those of you who like to code, if you want to do a better simulation than this, I would love to have something better. You can notice the slowing down as we go further and further. Okay, so now I'm going to go back to the slides. Okay, so the next identity we need, and the last one we need from Pascal's triangle, is the sum of n choose k from k to n is n plus 1 choose k plus 1. There's a combinatorial story for this as well. I'm not going to really go through this, but if you look at some diagonals, if we look at 1 plus 2 plus 3 plus 4, that is 10. If we look at 1 plus 4 plus 10, that's 15. 1 plus 5, that's 6. It's basically saying if you go down along a diagonal and sum them, starting in the beginning, it's equal to the one immediately below and to the right. So proof. We're going to do induction on n. So we'll fix k. Well, the base case, if n equals k, there's nothing to prove. We basically just have 1 equals 1. And so now we do the induction step. And this is exactly follow your nose. You assume it holds for n, and then we have stuff for n, and then we add one more term, and then we just play some games. And by induction, this is just n plus 1 choose k plus 1. And now we can use the Pascal identity, and it follows through immediately. That's all math we need to analyze the German-Tank problem, the generalization. And it's this identity that allows us to succeed. How many people at econ majors are going deep in economics? Oh, this is wonderful. Okay. Great. But if you had been going deep in those subjects, you would realize you don't get nice closed form answers. And if you want to say, well, what would happen if I actually changed some of the tax rates or some of the capital gains rates? What would that do to the economy? You have very complex models, and you have to do a lot of simulations, and you get confidence intervals. It's really nice if you have an answer that has a closed form parameter. You can just tweak this and say, I'm going to just tweak this and see how things change. Come on in. There's pizza up in the front. All right. So let's do the original version of the German tank problem. So, how should n hat, our best estimate for the maximum number of tanks, depend on the maximum number we observe m and the number of tanks we observe k? So I want to try to glean the formula. What would you guess? Give me some information about what the formula must look like. What kind of relationships must be between n, m, and k?
If m goes up, n should go up.
Good. So as n increases, n should increase. Can you give me anything else about the size of n and m?
If k is really big and really closer to m.
Yeah, probably the larger k is, the closer m is to n. So maybe it goes up with m, down with k. Excellent. What else?
Should we figure it out?
It should be, well, okay, you were so close. You want to correct? It should be at least right. It should be at least as large as m. So we could write it as m plus g of mk. And the simplest guess for g of mk is maybe some constant times m over k. It's going to be something that will go up as m goes up, and it will go down as k goes up. And it will be at least as large as m. So I'm basically saying, I know I've got to be at least as large as m. Let me say the excess is this nice function g of mk. It turns out the answer is b equals 1, and we're missing a constant term. So it's m times 1 plus 1 over k minus 1. Whenever you see a formula in math, you should ask, is it reasonable? What could we do to try to see if this is reasonable? What case could we look at? Yes?
Send k to infinity, send m to infinity.
Okay, so one is to send both of them to infinity. If we send both of them to infinity, what's going to happen?
Also independently of each other.
I'm sorry?
Independently of each other.
Independently of each other. Okay. So if we send, we're fixing n and sending n to infinity?
Sure.
Okay. And then this is basically telling us m is going to be related to n, it's going to be growing with n. But is that 1 plus 1 over k, is that the right growth rate? Well, it's going to be, I guess, n divided by n. So can you think of any extreme cases that might be worth studying? Yes?
M equals k.
We don't know what, I mean, if we choose k, we don't necessarily know what m is going to be. We observe that in the lab. So you have to tell me what would be a good value for k. The things we get to choose are n, the number of tanks, and k, the number of tanks we observe. So what would be a good value of k? K equals 1. If there's only one tank, well, then we would get, the best guess is essentially twice m. Well, if you only have one guess, where do you think that guess is going to be on the scale of 1 to n? Probably somewhere in the middle. So that's reasonable. There's another choice of k that's very reasonable. There's one more extreme case.
N?
Yeah, if you take k equals n, then you've observed every single tank. If k equals n, you will get that m has to be n. It's forced upon you. And then you will actually get that the formula works perfectly. So this gives us some confidence that this might actually be the right formula. So again, whenever you can do a sanity check, do a sanity check. So here's the key level. Let m be the random variable, so we're now going to use probability language to show you that I actually learned something here. Let m be the random variable for the maximum number observed. And little m is going to be the value. And then what we can do is we can calculate what is the probability that we take on the value of little m. And I claim that there's two different ways of looking at it. And the first thing is to note is that little m has to be between k and big M. Since we observe k tanks and the number from 1 onward, we can't observe our largest value less than k. And since the largest tank is numbered n, we're not going to observe something larger than n. So these are the ranges. And the first way of looking at it, it's m choose k minus n minus 1 choose k over n choose k. Well, how many ways can I choose k tanks from n? That's n choose k. I want to choose such that the largest tank is labeled m. M choose k is the number of ways to choose k tanks so that no tank is labeled larger than m. M minus 1 choose k is the number of ways to choose k tanks so that nothing is labeled larger than m minus 1. So the difference will be all the things that are labeled no more than m and have m as their largest. The other way of looking at it, which is the far right over here, is let's force one of the tanks to be M. Now we have to choose k minus 1 additional tanks from the m minus 1 numbers. You could actually use this as a story proof of Pascal's identity. Okay, so the text below is just explaining what that was. So now the notion of expected value. So everybody should be familiar with expected value, from taking classes and knowing what is the mean. How did I do relative to the mean? If you really care about what might you want to know, in addition to the mean. The variance, the standard deviation, how spread out it is. We actually don't need this for the talk. If you went to Harvard, you would be extremely concerned about your academic performance, and you would want to know also the skewness and the kurtosis. And so I actually was visiting a friend of mine at Harvard, and they listed, with all the names removed and just identifying numbers, people's grades, and then they wrote down, here's the mean, here's the standard deviation, here's the skewness, and here's the kurtosis, so that you could really see how you did relative to everyone else in the class. This is the same school where 93% of the students graduated with honors at one point in 1 year. And I think it was Dean Broadhead at Yale remarked to the press, I'd like to talk to the 7% who didn't and say, so what happened? But mean is the only concept we're going to need here, but there are others if you want to get a better sense of shape of how spread out you are. It's the average value. So what I do is for every value that big M can take on, I take that value and I weight it by the probability it occurs. And so if we substitute, because we know what the probability of M being N is, we get the following. So the further you go in mathematics, the more you learn that it's starting to scream at you. So when you see an M times an M minus 1, choose K minus 1, what is this screaming at you to do? I'm sorry?
Move it in.
Yeah, move it in. So basically, let's just expand everything else. So the algebra is really follow your nose. So I expand out the factorials. The M comes up over here. I have a K factorial, a K minus 1 factorial over here. Okay, so if I put in a K over K, there's the extra K that I'm putting in over here and here. I then have things cancel. And now I have this sum over here. And I've pulled out all of the stuff that doesn't have any M dependence. And now what's nice is this is the second combinatorial identity. And this is the whole reason why the miracle happens and we get a nice closed form expression. Because we have an identity for this, it's just n plus 1, choose k plus 1. Well, now that we have that, we just expand things out and do some algebra. We have pizza over here for those who are coming in late. And so when we expand it out, now we start canceling things, and it's just algebra, and it just cancels wonderfully. So we know the expected value is k n plus 1 divided by k plus 1. So we can solve and get the best estimate for the number of tanks is the expected value of m times 1 plus 1 over k minus 1. And so if we put in the value we observed, little m, here's our prediction. And so it comes out really nice. So this was not original, this had been done before. The new part was trying to generalize. And so I'll go through this really quickly because I want to get to the fun stuff. So we want to look at the spread. So we're going to look at the difference between N2 and N1. And now here's where things get annoying. If your lowest tank is 3 and your largest tank is 5, how many tanks do you have? Right, this is not a hard problem, right? But 5 minus 3 is 2. So you have to remember that, there's this extra plus 1. And just a real annoyance. Now, if you have a large number of tanks, does a plus 1 really matter? If there's 2,000 tanks in the field and you're off by 1, is it a big deal? No. Now, there is something else in World War I where estimating is extremely important, and being off by 1 would be tremendous. Anybody know what weapon this was? Nuclear weapons. So when we dropped the second bomb on Japan, how many nuclear weapons did the US have in reserve? 0. That was it. It's poker face time. Okay? Now, we could build more nuclear weapons, but we only had 2 at that point. And so there was real concern. If we drop the second one, we're not going to have another one available for a little bit of time. In a situation when you only have 2 objects, being off by 1 or 2 is significant. When you have 1,000, being off by 1 is not bad at all. So we can play the same game as before. And again, what is the best guess for the spread for the number of tanks as a function of the smallest and the largest values observed? And so we play a game similar as before, and we get this best guess is the spread 1 plus 2 over k minus 1 minus 1. And we can try extreme cases before, it's good. The 2 looks nice, because now we have 2 directions we're going. And so I kind of like the 2, that makes me happy. Do you like the k minus 1? Would you have expected a k and not a k minus 1? So how many of you have taken a stats class? I guess things haven't changed that much since I was here. Strongly urge you to take a stats class. So if you take a stats class, you start talking about population standard deviations. And you don't always divide by n, you often divide by n-1. Imagine you're trying to calculate the spread, and you only have one observation. Should you be able to say anything about the spread? No. If you're trying to calculate the variance in the class, and you only have one observation on the performance, you should not have any understanding at all of what the variance is, or what the standard deviation is. So your formula should come crashing down. That's actually good that it comes crashing down when k equals 1. So the proof is very similar. We now can construct a formula similar to before as to what is the probability the spread is exactly a little less, and then we just go through the algebra. It's exactly as before. So if anybody's interested, you can email me. I will send you the draft of the paper. The slides will also be online. I will send it to one of the officers who can distribute as. So the rest of the proof, as I said, is very similar. You get to do a lot of multiplying by 1 and adding 0. Anybody take a class from Professor Jones? No? Okay. Well, when I was here, he really hammered home the power of multiplying by 1 or adding 0. And then I remember when he goes, you know, the log of 1 is 0. There's really only one thing you can do in mathematics. And it's amazing how much of math is doing good algebraic simplifications. And doing this logarithmic transformation, actually multiplying by 1 and adding 0 is essentially the same. We will see a logarithmic transformation later. If I wanted to be suspenseful, I could hide the actual results, but we all know the mathematicians did much better than the Spies. I'm giving the talk. How much better? Essentially the order of magnitude. So when you look at how much the mathematicians and the statisticians were estimating, and what the Spies were estimating, and what the Germans actually were building, the mathematicians were doing a great job. I'm not sure if they called themselves statisticians back then. I'll have to check. Now, the real issue in something like that, how many of you are considering a career in consulting? Interesting. Okay. No wonder Harvard's a down this beating house. Okay. It's not enough to just have the right answer. You have to convince the person who can say yay or nay that they should trust you. And so the very hard thing in a situation like this is, how do you convince someone that your analysis is right? One of the books I wrote is on cryptography, and I have a picture of Midway. So this is the Pacific Theater. I know the talk is mostly in the European theater, but it has one of my favorite stories of applied mathematics, cryptography and breaking codes. So the US had broken much of the Japanese code, and we knew the Japanese were planning on attacking something they designated AF-15. And at this point, the Pacific War is not going well for the US. And the Japanese have more aircraft carriers than us. But we know their plan. We have the option and the ability to have an ambush. That's, of course, if AF-15 is actually Midway. If AF-15 is Australia or the West Coast or Hawaii, we have our ships in the wrong spot, and it's another humiliating defeat. So the cryptography people go to Admiral Nimitz, and they say, we're pretty sure they're going to be attacking Midway, and we think this is what they're going to be doing. You're pretty sure. Come back when you're sure. And so the way they became sure was one of the most clever ideas I've heard in my life. On a secure channel, they contacted Midway, and they said, we want you to break one of your water pumps, and then report back either in the open or on a frequency we know the Japanese have cracked that you have a broken water pump. A day or two later, the Americans intercept a Japanese message. The Japanese message says, we have just intercepted an American message from AF-15. They have a broken water pump, and will be out of fresh water in 2 weeks if they don't get a replacement. At which point it says, I'm in, let's do it. And it was the turning point in the Pacific Theater. So you do not often need to know a tremendous amount of mathematics to make a difference. But you have to be able to convince people to trust you. And that's one of the skills that I really like to hop on when I give talks is to, what can you do so that somebody will believe you? So what I want to do now is, since most of you have not seen statistics, this is a good opportunity to give you a quick introduction to how a mathematician views statistics. So there are 3 different ways we can measure errors. So oftentimes we believe that there's a linear relationship. How many people are doing physics? At least 4 hands up. So you eventually learn in physics that essentially everything in the world is a linear oscillator. Yes? All right, there we go. Okay, finally, yes. Okay, so nothing Nothing has changed since I was here, okay? You just do the linear oscillator again and again and again. Maybe you have a linear oscillator on a linear oscillator, you 0 to 3, okay? But you can use everything to that. So we start off with assuming a linear relationship. You know, y is ax plus b. And here are three notions of error. We could look at the observed value, yi minus the predicted. We could look at the absolute value of the observed minus predicted, or we could look at the square. Can somebody tell me what is wrong with the first method? Why is that bad? Yes?
Then like positive and negative errors.
Yes, positive error, negative errors can cancel. Now this will not show on the screen over here, but if I draw something on a square, I have lower left and upper right, what's the best fit line? Yes, exactly. Starting in the other corner and going straight back and down so that these two errors perfectly cancel and you have zero error. If you want, you can even have negative error. Okay, so we all agree that the first one is right on. What about the second? Should we use the second? Should we use absolute values, or should we use the third, which has squares? Any thoughts?
Perhaps we should use the squares, because like if you're using absolute values, you're measuring it like up where the curve is there, not like the closest.
We were still measuring it up. It's just, do we keep that value, do we square that value? I mean, the absolute value is the difference between the observed and the predicted. Why would we square things? Am I just trying to give you an alternative so that we can have a discussion and discard it? Or is there something good about it?
Is the squares the only way like a unique solution?
I'm not sure about that. That's a good point. I'm not sure about that.
When you square, like if there's a large error, it's like emphasizable.
Okay, so if there's a large error, it's emphasizable. Is that a good thing or a bad thing? So now if you have one bad observation, you know, you're observing data points. That's true. Right. If you have that one observation that's terrible, it's going to skew your whole data. So that is a point against the mean for 2. There is a 0.43 over 2.
If you're trying to minimize the error, it's easy to differentiate.
Yes.
Because it's not continuous.
Yes, so in fact, the absolute value function is not differentiable. So we can't use calculus. How many of you have taken a calculus class? Oh, you've taken 2 calculus classes, 3 calculus classes. Okay, yes. We've done all of this calculus. Wouldn't it be nice to use it? Right? There's a reason for taking these classes. So if we use calculus, you feel better. What do you take after calculus?
Real analysis.
You go straight from calculus to real analysis? Okay, in Europe I can see that. What do you normally do in America after calculus? Linear algebra. And so by using calculus and linear algebra together, we can actually get a unique solution, and it's an easy solution. So the way it works is you take the error function, it's a function of a and b, and you set the 2 partial derivatives with respect to a and b to be 0. And those are the conditions for an extreme integral. And then when you solve, you actually get a system of linear equations for the unknowns a and b, and when you solve, you get explicit formulas in terms of the observations. The important thing to remember is the x's and the y's are your data and your observations, the a and the b are the unknown parameters. There's an explicit formula. So now, most relationships in the world are not linear, but they can frequently be transformed to linear. So if I have y equals bx to the a, if I take the log of both sides, the log of y is a log x plus b. How many of you have ever heard any justification for why you learn logarithms? Not many hands are going up. There is a reason why we teach you logarithms. It allows us to convert nonlinear relationships to linear, and then we can use these systems. So if you do like Newton's law of gravity, g m1 and 2 over r squared, and you want to see how does gravity depend on the distance, it's a nonlinear relationship. But if you do this logarithmic change, it will be linear. Newton was inspired by Kepler's 3 laws of planetary motion. The first is, anybody remember the first one? We have a couple of physics people here. Orbits are elliptical. Good, that's 1. 2. Equal area and equal time. And 3 is the more complicated. If t is the orbital period of a planet traveling an elliptical orbit about the sun, and no other objects exist, that's important, then the period squared is proportional to the length cubed, where L is the length of the sum of major axis. This is almost like Sesame Street. One of these laws is not like the other. A little bit different. Now, t squared equals b tilde L cubed. Whenever you see a tilde, that should tell you that this is a constant that's not going to survive long. Right? And so I can take the square root of both sides, and I'll replace b tilde with b, and I'll get t equals b L to the 1.5. Really, I don't have to have two different exponents. I can always adjust it to have t be to the first power. Assume we don't know this. Assume we don't know it's to the 1.5. Assume we just think it's b L to the a. Can we figure out what b and a are? Now, one thing that has changed since I was an undergraduate here is the number of planets in the solar system. We went from a high of 9 down to the current value of 8. Okay. I actually know somebody who knows the person who hit enter to officially downgrade Pluto's status on the international database. So I'm giving you the orbital periods in years, and I'm giving you the length of the semi-major axes in astronomical units. And we'll talk a little bit about why we're using these units. There's a lot of fun units in the world. There are the Bruno, the millihellen, the slug, the snoot. I'll talk about some of them. Anybody want to guess what A should be? Or what B should be? Well, A is the hard one. We're going to say it's 1.5. Any thoughts about what B should be from this data?
1.
Excellent. Why should it be 1?
You choose your units.
Yeah, I'm choosing my units. You know, orbital period is in years, and the semi-major axis is in astronomical units, which is basically the distance from the Earth to the Sun. It's not quite because, unfortunately, we have leap days and all that crap. But if you highlight these in red, you can see that B should probably be 1. And if you plot, you do this log-log plot, it's incredible how great it fits. And we get a best fit line of A is 1.49986 and B is 0.0001. Well, if capital B is 1, the log of 1 is 0, this is really good. It is amazing how good this data is. And again, the prediction was based on no other objects in the universe. So the different planets will have small impacts on each other, so we shouldn't expect a perfect value here. So this is actually phenomenally good. I will just mention a little bit about some of my favorite units. I'll mention the snoot. Anybody know what the snoot is? Excellent. So this is the Harvard Bridge. It's about 620.1 meters, or it's 364.1 snoots plus or minus a year. So Snoot, at one point in his life, was a freshman at MIT, and he was pledging to a fraternity. And the fraternity wanted, how long was this bridge in snoots? So they would pick him up, mark, pick him up, mark, pick him up, mark, and they found the bridge was 364.1, but I love the plus or minus in here. Cambridge was not amused, and they painted over the lines. Well, the fraternities wouldn't have any of that, so they got Snoot back. And it went back and forth for a while, and eventually, this is those damn MIT kids, and they just threw up their hands. Things have changed to the point now where these markings are now institutionalized. And when there are accidents on the bridge, they reported at the Snoot mark. There was a car crash at 238.7 snoots. That's wonderful. Now, you may be wondering, what happened to Snoot? So the exciting conclusion of the talk will be, what happened to his life? I mean, could there be anything better than being a unit of measurement? So what I want to do is I want to talk a little bit about how you can use data to glean things. So the birthday problem, imagine you have, everybody has equal likelihood of having any day in the year as their birthday. How many people do you need to have in a room before you have roughly 2 people? If you have 365 days in the year, you need around 22. If you have D days in the year, it turns out it's approximately D to the 1/2 and the square root of log 4. It's a nice exercise to prove that. The real important part here is how it depends on the number of days in the year. It depends like the square root of the number of days. One year when I was doing a recruiting event for Williams, I got permission from the director of admissions to give free admission to everyone at my table if there weren't 2 people who shared a birthday in the room. I said, I'll even provide half the money. I did not tell my wife at the time. I shouldn't forget. She's still my wife. She wasn't just my wife at the time. There were over 100 people in the room. I was not worried. I showed the dean the calculation. I showed how many 9s we have. It's 0.9999999 likely that. So great problem to do. Here's a little plot. And so again, when we look at things, when we do the simulations, I did 2 sets of 10,000. A should be about 1/2. We get 0.506 and 0.481. Not so bad. Now the B's, are a little bit off. And this is telling you that this method is doing a better job of getting the exponent than getting that little multiplicative constant. When you think about taking it as a log scale, it's a little shift here. That shift is not going to have a huge impact. It's going to be harder to measure that. So we're getting the right value correct. This is our first guess of the German tank problem, which just sucks. I mean, there's no good way to phrase it. So we're plotting n minus m. We know there has to be at least m tanks if we observe m. So we're plotting the excess from what we must have as a function of m over k, which is what it should depend on. And we see it's just terrible. You know, the best fit value. So let's try doing some other things. So I did a log plot, and I plotted against log of m and 1 over k, and you can see a nice two-dimensional plane. So I'm not going to go into too much detail. I want to emphasize something else for the last few minutes. But if you look at it the right way, it does a good job. Let's look at it the wrong way. So what I'm going to do now is I'm going to plot n versus the maximum, so the x-axis is the maximum observed tank for k equals 1. Theory says n should be twice m minus 1. The best fit line is 0.784 m plus 2,875. Now, do you think this formula can work as n goes to infinity? What is screaming absurdity at you? There's something wrong with this formula.
Your system has to be lower than your max number.
Yes. When you observe m, in the limit, you're saying there's approximately 78% of m is how many tanks we have. So wait, we observed 1 million tanks, and you're saying there's about 784,000? Yes. And then if you were doing consulting, then you would give them a large bill. So we can look at k equals 2. The best fit line is 1.5 m minus 1. We get 0.964. Still sucks. We can take k equals 5. It's getting better. It should be 1.2 m. We're getting 1.037 m. It's at least over 1. Now we can do it the other way around. Let's plot m versus the number of tanks. When we do it this way, theory says m should be 0.5n plus 0.5, and the best fit is 0.496n plus 10.5. When we do it that way, it's actually much better. The same thing if we do it with k equals 2, we get 0.667 versus 0.668. To me, that's a success. Yes, we're off by a little bit, but when we're talking about on the order of 1,000, 10,000 tanks, being off in a constant term of 9, not a big deal. When we do k equals 5, again, not a big deal for what we're getting for the error. Here's another fun way to look at it. What I'm going to do now is, for each n, what I'm going to do is I'm going to do 100 different runs for each n and then record the value. So I'm doing some type of averaging. And when I do that, it compactifies the graph. And now we get theory predicts 1.5 m minus 1. We're getting 1.496 m plus 171. So there's some advanced techniques you can do to try to clean up bad data and make better predictions. I want to end with sniffing out a formula. So we said it should be m plus m over k. How can we sniff out that 1 over k? Well, what I'm going to do is I'm going to plot the slope a versus k. So k is the number of tanks we observe. So we can observe 1 tank, 2 tanks, 3 tanks. And we'll take the best fit value for the slopes. When you look at this, can anybody look at this and tell me what curve that is?
Is that 1 over x?
Yes, it should be 1 over x because theory says it should be 1 over k. So it should be 1 over x. If you didn't see that it was 1 over k, would you still say 1 over x, or could it be 1 over x to the 1.1? Could you see the difference? Could there be some logs? It would be hard to get exactly what it is. Can anybody give me a lower bound for the slope? It has to be at least. What's the smallest a could be of any value of k? We're inflating our m by some number. So a has to be at least as large as 1. So since we know a has to be at least 1, let's look at a plot of a minus 1. And so we're going to do a log plot of a minus 1 versus k. That's a pretty good straight line. And when you do the best fit slope, you get negative 0.999 log k minus 007. Okay. He actually was active all the way back in World War II. This is pretty close to 1 over k. This is almost negative 1, and we should have 0. We have 0.007. That's not bad. All right. So before we get to the references, some advice. Seize opportunities. You never know where they will lead. So we mentioned Smoot. This is not from his college days. This is from his later in life career days. Does anybody know what happened to Smoot? Yes.
For the ISO board units.
More than just a number.
Oh, it was like the chair.
Yes. Chairman of the American National. You can't make this up. I'm just imagining his application. Well, I don't like to brag, but I am a unit of measurement. I am sure that for years it was a great story for him in many conversations. It's a way to. So at Williams, we have a wonderful tradition called winter study, where for 4 months students ski and occasionally go to class for a little bit each day. And professors teach a variety of things. One of my colleagues teaches wine tasting in France. Another colleague teaches how do you make beer. You might be detecting a theme. Another teaches photography. One does national parks. One year I did cryptography. And I encrypted the title of the course using the Caesar cipher, just shifting every letter forward by 3. And I was contacted by the registrar and said, this has to be a mistake. You don't really want this on our students' transcripts. He goes, I do. When they apply for jobs, it's going to be a conversational start. And it was. So it was, you were right, Professor. Well, they said, we were looking at your transcript. Like, what the hell? But when you can, you want to try to shift the conversation to an area where you have the strength. So thank you.